Welcome to this lesson. Today we'll be treating dimensional analysis. So in the previous lesson we talked about quantities and also we talked about units. So in this lesson we'll be treating dimensional analysis. So now, dimensional analysis is the method used to check the consistency of physical equations and to derive relationships between physical quantities. So when you are asked to carry out a dimensional analysis, the purpose of doing that is to try to see how a particular function or a particular quantity is correct, how correct a particular quantity is. So when you carry out dimensional analysis, you can see if a particular equation or particular quantity in an equation, if it is actually correct, because when you are carrying out dimensional analysis, you're trying to align to see if all the units are balanced properly. So probably in one of our lessons we'll see how to solve for dimensional analysis, or say in this in this line, I have here that it is based on the idea of physical quantities can be. So it is based on that idea that physical quantities can be expressed in terms of their fundamental dimensions, such as mass, length, and time. So, as much as we talk about dimensional analysis, we need to know how these how dimensions are being represented. So dimensions are being represented in terms of mass, length, and time. So unlike units, in units we talk about kilogram, we talk about meters, we talk about second. But for dimension, we're talking about mass, length, and time. So when you talk about dimension, you're talking about mass, length, and time. So when you are given probably an expression, say velocity, we have velocity being velocity equal to distance over time. In terms of units, it's going to be equal to meters over second. That's meters per second. But in terms of dimension, it would no longer, you need to change meters to its fundamental expression. So in that case, you'll be having, instead of meter, you'll be having length, because meter is a measure of length. Then in the case of second, instead of second, you'll be having time, so that you can now say this is equal to length time raised power, using it in indical expression, raised power minus 1. So that's how dimension varies from units. So dimensions are trying to express things in their initial fundamental quantity. So now let's move on to the next slide. This is just an introduction. So let's move on to the next slide. So we have length, mass, and time. So these are like the fundamental units, or the fundamental physical quantities of in physics. So length, as I said, it is represented in L with the letter L. Mass is represented with the letter M. T is represented with the letter T. So the fundamental dimension that is used to describe distance, size, and displacement is length. So for mass, it is used to measure weight. Mass is used to measure weight, used to measure force. It's involved when you're trying to measure force, because you need to have a mass and stuff like that. So while time is used to check duration of how things have how time passes. So time is used to measure duration of an event. So let's see let's just move on to the next slide first. The importance of dimensional analysis. Dimensional analysis helps to try to convert, it tries to help in converting between different units. It tries to help to convert between different units. And it tries to ensure correctness of equation. So as I was trying to say, dimensional analysis can be used to check whether a particular equation is correct. So let me explain what I mean by that. Let's say we had this equation now. We had the equation saying maybe a plus b being equal to c. If the unit of c is equal to kilogram per second, it means the unit of a and the unit of b should be able to balance off to be equal to this. So that's when you're trying to carry out dimensional analysis. So it's important to take note that once you have plus, whatsoever is between any plus should have equal dimension with what is on the other side of the plus. So what do I mean by that? If you had a plus B plus C plus D. It means the dimension of A must be equal to the dimension of B, must be equal to the dimension of C, and must be equal to the dimension of D, because they are separated apart by plus. So even plus and minus, they do the same thing. So if it is minus, the dimension of A must be equal to the dimension of B and equal to C and equal to D. But if it's to be multiplication, that's how we have A times B. What you do to the dimension is you combine the dimension. Say the dimension of A was kilogram and dimension of B was second. Was mass, that is representing the unit of A is kilogram and the unit of B is second. If you wanted to represent the dimension, you will be joining both of them. So you'll be having something like kilogram second, because they are separated by multiplication sign. So now, how does this help? So if you had this expression here and we said it's all equal to maybe Q, it means this one's unit will be equal to this one's unit, equals to this one's unit, equal to this one's unit, and equals to also this one's unit. So, but in the case of multiplication now, as we had, so say we had Q and we had A times B times C. A was probably kilogram, B is probably say B is let's say meter, and C is probably second. It means since they are separated by multiplication, it means when you are trying to get the dimensional analysis, I said when you have multiplication in between them, you will join them together. So you just join these three together. So you'll be having K, G, M, S. And because of this is the unit on the left hand side, it must always balance with the unit on the right hand side. So you can automatically say that the unit of this one should be equal to K, G, M, S. So because of the ones on the left hand side, the aggregate of the ones on the left hand side must be equal to the aggregate of the ones on the right hand side. So let's move on to our next slide. Probably in further learning, we would be able to understand this properly. So now we'll talk about weight and mass. So weight and mass, they sound very alike, but they are not actually the same thing. Weight is actually a vector quantity, while mass is a scalar quantity, but we're not yet treating scalar and vector quantity, but just take that at the back of your mind. So when we get to vector quantities and scalar quantities, you can be able to remember and probably pay attention when we try to explain the differences between these two. So mass is the amount of matter in an object, while weight is the force exerted by gravity on that mass. So mass exists as an object exists, while weight is the force that acts on that existing object. So it's just as though like this now. Say we have an object here. The mass of that object is how much it occupies, how much the particle occupies, or how much particles are present. That's what the mass is. So now the weight is now how much force is exerted on this object to make it heavy. So that's what will determine the weight. So we could have millions of particles inside and its weight will still be less. Its weight will still be less because gravity exerts less force on it. So, but we can have that same quantity of atoms or particles inside this and its weight will be higher because gravity exerts more force on that. So the weight of an object depends on the location because gravity varies. So objects could weigh differently when you move to different locations, but mass remains constant. That's the quantity of atoms present in that particular object. It remains constant. So this distinction is very important when you're trying to talk about physics. So let's move on to our next slide. So applications of dimensional analysis. So as I was talking about dimensional analysis, I said it is used to check the consistency of equation. This is one of the key function of dimensional analysis, is used to check the consistency of equations. So the next is also used for the conversion of units. So when we are trying to do unit conversions, dimensional analysis is necessary because it helps us it guides us. It's like a rail guard that tries to help us know when we are going off bounds or when we are doing what is not really right. So another function of or another application of the dimensional analysis is used to derive relationship between physical quantities. So as I was trying to say that when you have A plus B plus C, we can say that because A plus B plus C, they are added together, they have a relationship and their units are going to be definitely the same. Even if A is not looking like B and C is not looking like C, but because of they have the same unit, we can say that there's a relationship between them. So it also helps to in approximating the values of quantities in cases of in cases where experimental data are lacking. So now let's move on to the next slide. To understand dimensional analysis, we need to know some of the basics of dimensioning, which are that masses are represented with weights are the masses are represented with kilogram and letter m. We are trying to carry out the dimensional analysis, and lengths are measured with, or length is measured with letter L, and T is measured with letter T. Time is measured with letter T. So dimensional analysis helps us to derive formulas for physical quantities by examining their fundamental dimension. So let's see some examples of how these things play out. Let's see how we can get the dimension of velocity. So velocity is distance over time, as I said initially. So distance is a measure of length. So because of it's a measure of length, we can see that distance is measured in length over time is measured in second. So over time, capital T. So now, because of the ones on the right hand side, the aggregate of everything here is length over time. It means the thing on the right hand side must also be equal to L over T. So we can say that because of the dimensional calculation of the right hand side gave L over T, that of the right hand side must always be equal to the same thing on the left hand side. So because of that, we'll just look at this. Okay, since we have only V, it means that we can say that the dimension of V automatically is the same as that of D over T. That is the same as length over time. So this is how we use dimensional analysis. So this method tries to provide a powerful way to establish the relationship between quantities without the need of detailed experimentation. So now, as in cases where you have, let me bring an example of a formula that can tell this better. I think S is equal to UT plus half AT squared. No, this one, since it's squared, it will become a little bit complicated. So let me use one of the basic one. V is equal to U plus AT. So we'll see it clearly. So these are laws of physics, laws of motion. So we have V is equal to U plus AT. So I said when you have plus, it means what is here is going to be equal to what is here. And what is here, because it's on the left hand side, must be equal to what's on the right hand side. So let's see how we can get the dimension of this. So we know that velocity is measured in, that's this one here. This U is measured in meters per second. A is measured in meters per second squared. T is measured in second. So now, from the law of this, now we could find the dimension of V. We can find the unit of V and even the dimension of V. So to find the dimension of V now, let's see how we'll do it. We know only this. So now, checking this now, since this is a plus, since this is separated with a plus, we can say that this one is equal to the unit of this without any experiment. Because this one also, the unit of this one will also be equal to this if you should find this. So this one, we have A and T separated by multiplication. So now let's see how it works. On this end, we have V equal to U is in meters over second. So plus A is in meters over second squared times S in second. So second will cancel out one of the second here. So we left with meters over second plus meters over second. So we can see that this is equal to this, and it's going to be equal to that for this. So because of the dimension, and this already is telling us that the equation is correct first, and next telling us the dimension of this unknown V. So that's how units and dimensions, or dimensional analysis in general, is used in physics. So now let's move on to our next slide. In conclusion, this session we've been able to try to explore the dimensional analysis and its importance in ensuring consistent equations, and also its application in deriving formulas. So we've also tried to discuss the distinction between masses and weights, and also the role of dimensional analysis in understanding physical phenomena. So dimensional analysis can be used to derive the units of different unknown parameters. It can be used to derive the units of different unknown parameters. So that will be all for this lesson. I'm saying goodbye.